快了，你那拿车的时候讲 share over 可以抄。
对啊。
The white shirt.
能带。
Hey, class.
Actually, we are doing 2D, right? Yeah. So we want to draw this 2D. Just that. Should be 2D wire.
Okay. A few questions, class. First, what's your question? Can you just say it out loud?
So I think at first the trust will
We just
I have some reference.
just draw the skeleton. So the skeleton.
That's excellent. For the U1 and U2 for label number 2, and this part different. So compared to what the lecturer saw, so hence I asked him. Just give me a presentation. Yeah, this part and also.
No, you show just now the first one, the first question you asked.
The first.
The simple result.
Okay, the resultant force for each one is facing outwards. When you look at mine, it's facing inwards.
No.
Class, the reaction force is which reaction force? How many reaction force you have for the 2D space? Two, correct. Is RF1 or RF2, correct? So RF1 is different.
Yeah.
RF2 is about the same.
Yeah.
RF1 is different.
Yeah.
So is it important? Huh?
Yes.
Look at the magnitude of RF1. What is how much Newton is that? Look at RF1.
That's right.
Okay, this one. RF1 is how much? 1.89
Basically 0.
is 0. Is E negative 13. Good point. So you are saying that mine is 0.00001, that is 0.0002.
Yeah.
There's no difference.
But sometimes you
Yeah.
do the same results.
Yeah, but it's
Why is having a different result?
Because
Yeah.
in this sort of software, right, what it's doing is, when you do your matrix transfer, right, your matrix inverse, correct, there will be truncation error, especially when you do matrix inverse. Abacus handle about 16 decimal place, if I'm not wrong. Okay, about 16 decimal place. So there will be some part you do a truncation. So that's why you have very, very small difference. Okay?
But we follow you, but why is it still different?
Yeah, it could be anything lah. It could be like your axis, your x-axis, y-axis is different. Yeah, your coordinate is different. Yeah,
So it's okay.
it's okay because your 0 is different from my 0.
Yeah.
Both of them are 0, so it doesn't matter.
Then it's
But if RF2 is different, is it important?
Yes.
If R1 is different, is it important?
No.
No. Very good. Okay, next one.
Okay, R2 is fine.
Yeah. The next question. Yeah. Okay.
This one is different.
Yeah. What you are saying, correct me if I'm wrong, what you're saying is that your node 2 result is different from my
Yeah.
node 2 result, correct? Is that important?
Yes.
Provided your node 2 and my node 2 is the same node 2. It's definitely not the same node 2. Exactly. So you know what I mean? Go back to can you have your, go back to this. Okay, I have checked just now what you say, right? It's about 4.6 millimeter for this node.
Yeah.
So most of it should be okay already. Okay. So your node 2 this is your element.
Element.
1. you go and compare you go and match back my note, the same note. Okay?
Yeah, it's
because
not the same.
the note label must be the same.
It's not the same.
Yeah, you know what I try to say? Because Abacus, when you name it, right, they do it automatically. So they do it, the way they do it is counterclockwise. But then it depends on which one you draw first, okay? So your note 2 and my note 2 could be different, so it doesn't matter. So just check back the same note 2. Let's say, for example, I want to check in this note. So mine may be note 3, yours may be note 1. Then we need to check the same note, okay? But that was a good observation. Important, but you need to tell difference, okay? Okay? Good. I see that you all have done it. I think that was a very comforting thought.
So how you want to do the so rectangle space, you want to do below the circumference circle. This is 2D, right? Yeah, 2D. So your rectangular frame, how you want to put it?
No, you don't need to.
Yeah, don't need to circle, but just say, because you have to know the rectangular
Trust that you have the same number.
people can translate into this. Right, so you how you want to draw the rectangular frame? Like below the diameter or
In your
No.
in in the PowerPoint that I show, right, I expect
yeah, but then you need to bring over to the 2D, then bring over to 3D. So you need to know the basics, like the parameters or how you want to fit it.
So you see in your
Because this, if I'm not wrong, we just took the.
in your report, right, you're supposed to give it in the tabular format also. Okay, in my work life, I do that also. You cannot just give them the image. The image is important. Let them have a feel how is the model deforming. That is important. But then as an engineer, I want to know exactly what is the safety factor. So that's why you need to do it like this. Okay. Of course, truncate certain amount so that you don't need to give me the entire list also. Okay, just truncate certain some of the lines. Just show me what is the maximum minimum. Just show me what is the maximum, what is the minimum. You know, can? Okay. Okay, can. So anybody else for the example? I think it's good. A lot of you watch it, so I thought that didn't waste my time. I suffered 3 a.m. people like on my just the next day I died.
Translate 1D to 3D.
Yeah, that's a good point. Your you know when you need to assign the local axis in your beam, correct? Your local axis. Actually, it doesn't matter whether you have the same direction or different direction from me or not. Important is to know that is your S11, especially in the beam model. Okay, to know that is the S11. Okay, it could be different direction because I create it like this, you create it like this, So Abacus will take it as this way as a positive axis, So it just is notation. It doesn't that really doesn't matter.
Below, basically one below.
We are going to
The rectangle will be touching the tangent of the circle. So for both sides will be the same.
learning
So
guide
the will
again.
be in between the
And
tangent
I'm going to
of
go
both
into the plate and shell model.
So some will be at the tangent of here. Some tangent of here. This way you start starting frame. So invisible one will be here. We circle tangent, we circle tangent, right? This will be our starting frame. We draw for the 1D space.
Then if you want to draw the.
I hope you all understand one thing is that most important thing is to get the big pieces out first. Okay.
That means instead we can draw like this. Means we don't start with the circle. We start with the body.
Yeah, so the body, right? What I'm trying to do is because you need to translate to make it like same dimension, correct? For 1D, 2D, 3D, same dimension space. So right is the referencing point, right, will be the tangent of this circle and the tangent of this circle. Yeah. So that's how we start. Technically, you should put it like.
Later you should be wrong. Okay. I want to stress the most important part, right, is to get the big pieces first. Hey, class. So what is it? for your calculation, right? When you come to your first, the first two lessons, we talk about the directional method, right? So what's the main
Cannot base
part that you
distance we base on
main
we must
component
base
that
on
you
the
need to
angle.
know how to do? What's the main thing?
Sorry?
We must base on the angle.
That's
Think about
what- the main thing, right?
Chan, right?
In your
Yeah,
result,
so
when you
think about the
show
frame first.
me,
The
show
framing
me
size will be
to,
something like
form
that.
the
So you base
global
on
matrix.
this frame you do instead of
Okay?
like
So that's the most important thing.
So basically,
Of
what
course,
I'm saying
every
is
problem you need to draw something. Okay, but the main thing when it comes to that directional metric method,
It's not
right?
metric,
the-
is it
the-
reverse?
the
so basically our length right will be
constructs the
One,
global
two,
signal matrix.
two.
That's the most important.
0.5.
Okay.
Then our
Beam and truss know how to do
design
the-
space will be 162.5.
know how to do the model, mesh it, so
That's
that
how
you
it's
attach it to
optional.
the IMP file. Okay,
So design space.
inside of that.
keep our design
Likewise,
space
the
at
plate and
162.5.
shell know how to do it first. I will stress that because inside the learning guide, there's also a lot of other things that's important. Like the meshing, like the hybrid element, all these are here also.
Yeah.
But this is
This one
important, but it's not as important as to get the basic right first. That's more important. But I want you all to go back and read this part also.
yeah. Okay, right, sorry. Maybe
Like say, next week is the last lesson. So you must think about it, where must you be at before next week, okay?
Smaller one is 21.6. So it's smaller.
Yeah, so that's why this, no, next week, the week after next. So next week is critical, next week you all must put in a lot of work, okay?
Then
No, but
We're going to this example called the skew plate.
wow. Actually, I just make
Can you all see?
smaller. Called the tangent. Then from there we can do our the 2D drawing instead, right?
Okay, so what is a skew plate? If you look at this, right?
no, we cannot do like that. We have to. I mean, if you want to do it like this, right? Then
This is the planar view. You look at it from the top. This is the skew plate. Okay?
This guy.
You put it flat and you apply your load on top of it. One end restrained, the other end roller. Okay? So, question. We talked about this just now. Same set of question. Now instead, I have restraint on both ends, restraint on the roller on this side and roller on this side. And restraint on this end. This model, can I do it in a 3D solid? Can I model it? Technically, can I model it as a 3D solid? Technically, don't say it's good or no good, but can I do it as a 3D solid? Yes or no?
Yes.
Yes. Can I do it as a 1D element? Yes or no? Yes? Are you sure? This is a skewed plate. If it's a square plate, like this, you can. But it's a skewed plate like this. Can you do that? No, why not?
What's the one dimension?
Louder. Yes. Correct. Here, if it's a rectangular plate, right? If it's a normal rectangular plate, right? And I load it and I restrict it at the end like this, okay? I can just prescribe a section profile. It's just weird. I just need to prescribe a plate section profile, correct? And run it. But because it's not right, imagine I need to draw a line like this across as the representative beam element. And this area here, the section modulus is going to be wrong. Agree? Agree? Okay? Can I model it as a plate element? Yes or no? When I model it as a plate element, what must I prescribe as the additional information? The thickness. Alright? Okay? Everybody understand or everybody agree? Second question. is this going to be a, who think that this is going to be a 2D model? Put your hand. Who think that this is going to be a 3D model? Put your hand, put your hand, put your hand. I'm going to ask those who never put out hand, what do you think it is 4D space? Who thinks it's a 2D model? Quickly, 2D, put your hand. 2D. Who think that this is a 3D model? Put your hand. Quickly. Why is it a 3D model?
Angle.
Quickly, quickly. Why? Why do you think it's a 3D model?
Angle.
Because got the angle of the.
Okay. I can still model it in the 2D space one. I can still model this at 2D space one. Huh? This is very, very important. Right? This is the most important thing. Right? It looks trivial, but this is the most important thing. You realize? Okay? If it is a 2D model, where will be the load? If it's a 2D model, what is my Cartesian coordinate? X and Y. It's got to be that, ma, because if not, I can't even model this, correct? The problem is, what about my load? Where will be the load? The load is which direction? Just say. Huh? Huh?
One.
Load is where? Which direction? X direction, X direction. But you see, it's not that. This is the load there. What is the axis of the load? Huh? Who say? Number 3 direction, correct. It's in the 3rd direction, correct, which is the Z direction, very good. Okay? So can you do this in the 2D space? No. So what must you do it at 3D space? Now, don't look at this. If I was to apply a load like this, okay? If I was to apply the load like this, this is extremely important and you must understand this. Okay? If I was to do the skew plate like this, still a skew plate, correct? Instead of adding the load like this, I add the load like this. Who think that this is going to be a 3D space? Put your hand. Who think that this could be a 2D space? Put your hand. So, what space is going to be? 4D. Huh? Because it's 3D or 2D space. 2D space. Who else? Who think that this is going to be a 2D space? Everybody. Who think? Who think they're going to be a 3D space? Okay? This is your x-axis, this is your y-axis, 2. Okay? In abacus, 1 x-axis, 2 is y-axis. Okay? This is your Cartesian coordinate. If this is the question, this can be done in a 2D space. Agree? Why? Because number 1, I didn't expect any deformation in the 3rd direction. Correct? Because there is no external force in the 3rd direction, so it doesn't matter. Right? I don't care what's happening in 3rd direction. There's no degree of freedom in 3rd direction. But in this case, we will expect deformation in the 3rd direction. Yes, because it's going to deflect in the 3rd direction. Agree? Okay? Okay, so let's start. Huh? Sorry. So as usual, we go to new document. Then we save as.
I'm not even saying what so our design space is this 15
I'm
times.
going to run through this model.
Then the length, I'm not sure how you do for the 1D.
And my objective is to run through this model, show you how to do it, right? So you will have a feel. Because I will assume that you already know how to do the beam model, the beam and the truss model. And we're going to do the plane. So that then you have a feel of how what's the difference. Okay?
When about this can I mean you can do as a power. Do you want to modify for here then probably then will be like this now.
Try not to have space in order
You want to
Yeah.
It means will be like, just how my honeycomb, right? That section that we modify will be that section rather than from the external. So this one is always right, and this one is the beam, right? So the section that we implement is from here onwards instead of here.
My objective for the rest of today, right, is to show
So our class will be
my intention is to show you this model and try to let you know the difference between a plate, the 2D solid from the plate model, plate and shell model, okay? The plate model.
So
Yeah, the plate model. My intention was to show you the plate model and try to let you differentiate what is the difference between the 2D solid model. Okay, that is my objective, and I'll show you one time here.
this will be
Because I think in the online part, sometimes it's hard for me to
this thing will be
explain
high.
sufficiently for everybody
That means
to
this
understand.
space will be low.
This space, right? If I explain online, I feel that you might not really understand that at all. Okay, so same thing when it comes to abacus, right? You must set, first thing to, most important thing to do is to set the work directory first, so that all the file is saved in one direction. You see that every time the default is in the abacus 10 file, so you must change that. So everything is saved in a single folder. Okay. Next, we will what is the first module we will be using? Class. Very hard, very good. I see all familiar, very good. So that use of skill part. Name, as usual, is not a problem. Now, next one. What will it be? Hurry up.
2D.
3D or 2D? Class. Who think is 3D? Put your hand. Who think is 2D? You will be 3D. Because same thing, what we are defining here is that you need to see that it is on the third dimension. Okay, but it's okay. You all get it slowly, you will understand. Like I say, always think back, class. When you have a problem with this, right, always think back what I said just now. Okay? Imagine, because now my load is in the out of plane direction, correct? Your smooth plane. But if I was doing as a tension, as a tension load over there, will it be 2D or 3D? 2D. Okay, so always remember that. This is very, very important. Okay. Look, on the other hand, if this problem, right, this tensile problem, right, if I do it in a 3D, can or not? Can. Will it run? Yes, it will run. Okay, it will still run. Okay, but just that preferably it should be in a 2D space. Okay. 3D deform. Is it deformable or rigid? Deformable. Uranium is typically your CFD. Okay. Would it be solid, shell, wire, or point?
Shell.
Huh? Who think is solid? Class, who think is solid? Put your hand. Who think is shell? Put your hand. I'm going to go around ask. Not shell, not solid. Then what is it? What is it? What is it? Huh? Who think is solid? Put your hand. Who think is solid?
Can be solid lah, but
No, yes, agree. Who think is shell? Put your hand. What is it? Then what is it? Good point there. It could be solid, it could be shell. But like I said, if it can be done in the shell, do you do it in the solid?
no.
No. If it can be done in the shell, do we do it in the solid or the shell? Shell. Okay. If it must be done in the solid, you jolly well show me that why it can be done in the solid. You know what I mean? Okay. But in this case, can it be a shell? It can be a shell. Then I will do it as a shell. Okay. So there's a few ways. It could be planar, extrusion, revolution, or sweep. Okay. So you see here, because this planar means what? Means I draw up as a plane. I just sketch out as the skew plane. If it's extrusion means what? I just draw one line, then extrude. Okay. It is revolution because this is a 3D space. So my shell technically need not be a flat piece. It could be a curve. Last time when I was out in the industry, I do a lot like when we model in the seabed. Okay, I don't model really the seabed. I just model a bed profile. Then we will use like a revolution or an extrusion type. We will literally model out a surface. Okay, so that could be an extrusion or a revolution. But in this case, we just need to draw the skew plate feature, the geometry. Okay, so you can planar. So it's 100 by 40, right? So typically about 200 will be good enough, roughly. Roughly. Then after that, like I say, we just need to roughly draw something. Okay? Then we will erase the constraint because I wanted here, I wanted it to be a steel plate, right? So it can't be a right angle. So I gave it constraint. Okay. But then because it's a steel plate, right? I need to have the top bottom same length, the left and right to be the same length, right? So I must let it be equal length. I'm not following the way that you write, so you all can. I mean, it doesn't really matter, so you, like I say, you just need to make sure that it works. Okay. Then after that, I need to put in the constraint, right? So this is 100, this is 100, this is 40, right? Then I can let me do it again. So this way is more complicated because I don't want to show. Okay, I just need to draw something. It's easier to draw something like this. Okay, just draw something like this first. Okay. Then because you wanted the angle here, you wanted the angle here, so you just draw something like this. Again, and the constraint this way is easier. Equal length. That's equal length. So rather than do the angle, this way is easier. Okay. Then after that, I just up to you. You can just do a line here, horizontal line. You can do it as a construction line also if you want. Actually, you can do it as a construction line. So, yeah, just do a horizontal construction line. So this line you see that is hatched. So it's not you're not using it. Angle is what? 30, huh? Yeah, good. So this is 30. So you just click here. Up to this line here. We put in 30. Okay? What else? You see, so this length is the shorter length is vertical, okay? So it's 40, and 100 is to the Cartesian coordinate. So we must let this be vertical.
Plus one. Plus one.
Okay? Then we create a dimension. You just keep on pulling it down and it becomes a horizontal dimension. Like this, 40. Okay? Okay, so you go to XY plane, you see, always look at this. So this is your Cartesian coordinate. In the 3D space, it looks like this. Okay? 2D space look like this. Okay? So after the part module, what's the next one we are doing? Next one, property. Very familiar already, right? Yep. Sorry, can you repeat that? Huh? I really what's it hanging?
System.
Oh. I will check.
So you want
Let me
are
take
you
out
crazy?
so that
I can do this. The circle just ignore the circle. Input and
Okay, so this is a so this is in millimeter, right? This is in so it's wrong, so you see, this is wrong. Yeah. I didn't read it carefully just now. So you see, this is what? This is 40 centimeter and this is 100 centimeter. So it cannot be in centimeter. It must be in either what? Millimeter or meter. So we need to do it in millimeter. In this case, I will probably do it in millimeter. So like because the previous one we do in meter, right? So this one we do it in millimeter. So must do it in either millimeter or meter. Cannot be in centimeter. So just expand this, the time we say like the order tree, expand this. Double click it. Then we just go back to edit. Feature, just choose this line, edit feature. Choose as 1000. Okay, and this time, change to 400. So this will be millimeter.
yeah.
Although this, okay, sorry, I'll do it in meter instead. I'll do it in meter because the learning guide, learning, I just do it.
So this is just
Okay, so it's different from your learning guide, or you wanted me to do it in meter, which is the same as your learning guide.
You take the center
Huh?
as
So is it?
the facing as the.
No lah, cannot. You don't have time. Yeah, you all prefer in meter or millimeter? Quickly.
So I checked
Meter, okay.
facing cannot be more than 60 degrees and must be less
You don't have time, seriously.
It must be more than 30 less than 60.
More problematic. So it's 0.4, and this will be 1. Notice that the green line doesn't really matter.
copy. You see in between 30 plus 60.
Or you just put all 60 or all 30.
Then it
45
asks you to
45.
regenerate and double click it.
45 degree angle.
Yeah, 45 also.
So this is a meter now.
Like the best.
But then 45 will become like a straight line.
Then regenerate.
The angle is here.
So
45.
you can check the distance. Okay, go to here, distance. Check the distance
I need to be
from here
opposite.
to this point here.
Sorry.
Okay.
Or if you want, you can add. But
You mirror it. You do one side, then you mirror the second side.
I mean, if you want a better one, maybe we can do this. But this
Go on the window.
The lines for what?
another basic one means it's in between the intersection points. Every intersection point is one line. This will be stronger.
45? 45 or more?
Then this will be 45, 45. Then this one will be 45. Then the extrusion will be all triangles.
Yeah. No, you just do different, something to do different.
So you see the component distance, right? In this direction is 1 meter. 1. Then 0.5, 0. Okay? So you see from here, 1 is the x-axis, 0.5 is the y-axis, 0 is the z-axis. Okay? Then we are going back to the property. Save it, then we go to property. So they use the Young model from 30 because this is in meter. So your stress is in megapascal or in Pascal?
Megapascal.
In Pascal, because it's Newton meter. Newton per meter square, so it must be Pascal. Okay? So it will be 30 E9. Okay?
How many base?
You all get this, you all get what I mean, right? It's Newton per meter square. If it's Newton per millimeter square, then you megapascal. Okay? Poisson ratio 0.3.
Maybe single.
Usually the angle give how much?
Then next, we'll be creating a section.
But the braces will be long and short.
Yeah.
Braces.
Based on the,
Okay.
the width.
Now, for the section, right? Would it be a solid plate, a solid shell, or is it a beam?
Shell.
So you must be a shell, okay? Then you see here, you ask you to prescribe the thickness. And they are using with a thickness of 8 millimeter, so it's 0.008. Okay, so this is, remember just now we said this, right? Remember this, right, is what we say here. This is this. Right, but we need to let him know. Because the third dimension, right, if you're doing it in the 3D solid, then you just model in here, correct? But in this case, it's only one plate. So you need to let the software know what is the thickness you're prescribing, and this is the thickness we are talking about here. Okay, this is important, we all see that. Remember, in the beam and solid, in the section, what do? We do it as a profile. We do a section profile, correct? So this case, we're doing a thickness. Okay? Then material one is what we have just now. Integration point is because, so imagine this, remember, in the beam model, what do? In the beam model, right, if you wanted to find the bending stress, there's no bending stress. You need to find the S11. Remember, in the beam model, we find the S11 at top and bottom because this is your bending stress, correct? So you need to find the S11 here and S11 here. From there, you determine what's the bending stress because it's not one singular stress like what we have in the truss model, correct? Likewise for here, right? This you're calculating the stress across the body. That's why there is a different integration point across the thickness. So that means they're calculating, but they're assuming it linear. Okay, so but likewise, like what we have previously in the beam model, the shell model, the plate model will also have bending stress across the thickness. You also need to find out what is the stress at the top fiber and the bottom fiber, and through the integration point. Okay, but keep it as a default. Then after that, we will assign.
Actually, if we design for
You see here,
design, that means
this is something
but we don't need to
quite important, but most likely will not be tested. So we see the definition here. We are doing middle of the surface. Remember, remember we project, right? What we're trying to do is to project. Right? This is what I model here. But I need to give it a thickness, correct? But this thickness, it could be in the middle, or it could be at the bottom, or it could be at the top. Correct? This thickness could be at the bottom, or could be at the middle of the top. Correct? When do you do it at the bottom? When do you do it at the bottom? Let's say, for example, you have a flange, you have a flange type
they
of,
want us to give
you know,
the design
there's something like this.
based on trust, but we don't
So you have
design
let's say for example you have a steel section here and you're putting in a steel slab here. This will be a shell element, correct? But then the section modulus cannot be at the middle already. It must be at the bottom. It must be at the top.
care about the distance, maybe the distance
Okay.
it's just different design.
It's the where it bend, where you are expecting, where you find the central of the neutral, what is the neutral axis. But in this case, we can just leave it at the middle. Okay, middle surface. Then what the green color means, you have assigned it properly. Like the beam section, you need to orientate where is the primary axis. Okay, so like the beam, whereby we need to access, in the beam model, we assign the beam orientation. In this case, we're assigning it the material orientation for the shell model. So this is the part that's different from your beam model. Okay, you need to assign the material section. You see, the default section, right? The default section is here. The default section means what? So remember, you have your inside your beam model, right? You have only one stress, S11, correct? In your shell model, in your plate model, does it only have S11? No. Why? You have S11 and S22. You have two because it's a plate, correct? In a solid, what do you have? S11, S22, and S33. You have all three. Okay? Can? But in this case, if I let my S11 and S22 be in this direction, is it correct? Answer is no. Why? Because I'm loading in this direction, correct? And my restriction is in this plate and this plate. So where is the longest span in this beam? Is it this direction or is it in this direction? Where is the longest span? Where is the longest span?
1.
Huh? 1 is the longest span. Now, where is the longest? But it's a good point. S11 and 1 is longer compared to the second direction. But actually, the longest span, right, is in this diagonal direction, isn't it? Correct? Because you're creating the support like this. So imagine the bending will be in this direction. The maximum stress will be in this direction. Because the maximum span is in this direction. Agree? Correct? From this point to this point is allowed to move. So this, I want to know the stress in this direction because that is the longest span that you have. Can? This is important but not necessary. That's necessary. No, not necessary that critical because unlikely you're going to test on that. I need to create so you need to create because the abacus does it right in a Cartesian coordinate. So you will always, of course, it will always go to the default one, which is 1, 2, and 3. But because this isn't our most critical one, our most critical is direction, so we must create another Cartesian coordinate. That's why you see I'm creating another Cartesian coordinate, another coordinate system. So is to have this as the x-axis instead. So I will have a single coordinate system. So that's what I'm creating now. So this will be the point, midpoint, then the x-axis, I just leave any point along here. Okay. So you see, now the xy, instead of this, now you become this x, y. Okay? And later on, I will use this as the reference when I create the material orientation. Because the beam is not important, as I created this. Why is truss and beam not important? Is truss and beam important for this or not? No, it's not. Because the truss and beam, right, S01 is always along your beam direction. Correct? It's always changing. But in this case, it's different because you could have a lot of plates. So you will always prefer same thing as your solid, same thing as your plate. When it comes to the solid and plate, right, the stress direction is always back to your Cartesian coordinate. Okay? So I will assign the material orientation and use the. You see when I select this, right, then that part will highlight. When I pick this, right, then this part will highlight. Okay?
Anyway, you need
Okay, so what we can do is we delete this part, then this one will be.
Now you see, now this become S11. Do you see that?
Then our working area will be this.
This,
Then this.
the sign color is pointing S11. And what is the S12? This direction. Okay? It's always right angle because of all circle. So you always be right angle.
This cannot be portrayed as a trans model.
Okay? The next thing is that this is important. Sometimes, and in your solid model, that's what you also need to do in your. We need to create a partition in your exam. Sometimes this is important. Let's say, for example, in this case, where will be the maximum stress? Let's say if I have a simply supported beam, if I have like a beam here, okay, where will be the maximum stress?
Center.
Huh?
Center.
In the middle, right? The middle will be maximum stress. But if you let Abacus mesh it, right? If you see, if I just let it mesh, I don't know whether it's going to come out like that, okay? But let's say I don't care, I just mesh it, right? Yeah, just mesh it. Sorry? Size you need to key in. I mean, up to you. You need to have an idea. You need to choose something. Yeah. You need to prescribe something that is appropriate. Yeah. So you see, yeah. So this is still about. Okay, this is on the right. So you see, does it mesh in the middle? Do you have a node in the middle? Abacus will only give you the result right at every node, so you have one node. It's like a direct statement method. Only the node will have a result because that's what you put inside your single matrix, right? In this case, you will not have any result at the middle. That's why sometimes we will do partition at the important point. If I want to know what's the result at the middle, I will need to draw a line there, and Abacus automatically will assign a node at that location. Okay. So that's what we're going to do. Go back to the part. We're going to do a partition. Okay. There's two ways to do the partition. In the 2D model, right, you do it as the planar. Okay. If not, it will be at the. You will be in the solid. Either way, you can do it here. Okay. So you see, actually, Abacus, you will have a point in the middle. So you just need to draw it. And now, because you have drawn a line there, right? Next time when you mesh, right, you always have a node at the middle. That's why we need to have we need to do a partition. Okay, so after that we can do the same thing. Go back to your exam. After we have finished our property, go back to your assembly, bring in the part.
Oh, that means
Okay, then bring in.
it might still be the same because the 3 points will also receive the loads.
The node will be in center.
No, it will still be at 3 points.
3 points.
Because now you got 3 points, then unless we convert to 1, that means. Yeah.
How one you can
Yeah, after that, go to your step.
But that doesn't make sense because
Yeah, linear perturbation.
So basically, you squeeze in, so the angle right, is
Then go to per node. So we put in the boundary condition first. Okay, so we just put it as a displacement. And I want to restrain right the end, this end here in both directions. Okay? So you see, this is exactly like what we have just now for the material. Now, if I was to assign like in the beam model, right, it will always assign in the Cartesian coordinate. So it will be 1 and 2 direction. But in this case, can we do that? No, we can't, because that restraint right at the end here, right, the roller is what is moved in this direction, not in the x direction. Okay, that's why we need to change it to make sure that it doesn't follow this U1. It must follow just now, the one that we have created there. Okay. And it's evident if you see it's evident. Okay, once I do it right, if I choose this, if I choose U1, U2, never mind. I just want to show example. So you see that this is in this direction. You see, it's in this direction. But I need it to be in this direction because the roller is free to move in that direction. Okay? For the other end, not for this end. Okay, so we need to edit that. You never restrict that. You restrict. Because in the question, right, you say this is a fully restrained. So even in the quotation, it needs to be restrained. Okay. So we just follow this, then take this. Then you see that it's restrained in this direction. You see that? Okay. Yeah. Yeah. You are doing the other side. Okay, same thing here. I create another one. In this case, right, it will be free to rotate in the. It will be free to move right in the what direction? It will be free to move in the. Sorry, it will only be restrained in the y direction. Correct. It will be restrained only in. It will free to move in x direction. So it will be free to move in this x direction. So I create another one. Choose this point. Okay, then I will choose the coordinate system here and I select this one. Okay, so I will just choose everything except for that. Okay. Then we will add the load. The load right will be a line load. Or it's a pressure load, sorry, it's a pressure load. Because this is important because previously you will always add it as a concentrated load. So this is a pressure load. This one. Okay, so you have a pressure load. Okay, so add this, you just click on the surface. It's important to note that you don't click. There is a difference. You cannot drag the whole thing because you will end up selecting the edge also, the line also. So we just click on the surface itself. Okay. Then you will see. It will ask you to choose whether is it the brown or is it the purple because it will ask you to apply the load normal to the surface. So if it's the top surface, right, it will be going downwards. If the bottom surface, it will be upwards. Okay. So you will see it's the brown or purple. Then you can see that if you rotate around, right, behind is the purple surface. Behind is the purple surface. you see that? In front is the ground surface. So we're adding it downwards, so it must be the ground surface.
Not too nicely.
We already have sample.
Can.
What?
Check with it.
Yeah. Because when I create just now, I should have shift it back to the origin. You're right.
And baseline model. Then we just compare baseline model between 2D and 3D.
Yeah, you just do it again. Yeah, just restart. Not worth it.
Leave at least with design. But design iteration.
Yeah, just restart. Most of the time, it's actually very fast. Okay? So we added the nodes.
Through this.
Okay? No, it's very fast. Actually, each of these is done like less than 8 minutes. You can be done the same.
Do it.
Then we go and create a mesh.
Trials actually right need to be a certain parameter. Then from there we can decide. That's all. You do one first.
Okay, the mesh size in this case is 0.1. So you see, this is 1 meter. This is 1 meter. Correct? If I put in the global size is 0.1, how many should I be expecting along this length? Roughly. Huh? About 10. Okay, so it's important for you to imagine that. Remember, if it's something that's bending, right, you typically have about 10, 8, 10 roughly. Then nobody going to give you a straight answer because you have. But then you probably need to be 8 or 10. Okay, so that's why it's 0.1. So roughly it will be 10. Then we need to assign the element type. So they're using S8R5. So you just whether is it S, I don't know whether is it, this is very important. To me, this is not very important, but in case you are wondering what, in case to give you more confidence what to select, right? Just now you see, in the shell model, right, it will be S4. Typically, we do an S4. Shell, S4, okay? 4 nodes. This is the first order element, meaning what? Only the nodes, remember we said only the nodes have a degree of freedom, only the nodes can move, only the nodes can move, only the nodes move, correct? But if it's a second order, means what? It's 1, 2, 3. That means each edge have one more. Okay, so how many? 1, 2, 3, 4, 5, 6, 7, 8. Correct? That's a second order element. Okay? And you have one more in the middle. Okay? But there is also a reduced integration. So the middle node is not so important, so you can S8R5. That's why they can also have an S8R5. In your case, right, always in your exam, just use the S4 as good enough. Okay? Why do you need to have a second order here? You can read your learning guide, so you can have a second order here, right? So that previously, your more element, right, will only have a straight line because there's no node in the middle. But with a node, that means you're expecting the gradient is important. You want to know like how it's been deformed like this. If not previously, you answered. You know, it could deform the same way, but now you have a gradient, so you will have a stress gradient across the element itself. Okay. Then likewise, go to the job, run the job.
2 weeks for this, 2 weeks
In
for
the
No,
in the in the
you got 2 weeks to do.
never mind, later towards the end I will say that.
Last week, Sunday.
Okay, class, are you all still listening? Or if it doesn't matter to you already, huh? Listening, right? Okay. Maybe it's important because, like I said, certain things I wanted to discuss during the class. I thought it's important. It's easy for us to discuss during the class. Okay. Remember just now in the beam and thrust model, it's always along the beam itself, correct? And like I said, in the plate and shell, in your solid model, it's always what? You no longer have just one element. So you need to know what is the stress along this plate. Okay? If you look into your if you look at the result, right, you see now there's S11, S22. Okay? Why is that S33? Yeah. But why is that S33? Because now we are allowing it to deflect in the third direction, so there will be also a shear across the thickness, the load. Okay? So there will be an S33. Okay? Yeah, so you see the problem is you don't really have a bending load. Because strictly speaking, the bending load, right, is what? Imagine this is the shell element, correct? Your bending load is the difference between your top fiber the load and your bottom fiber the load. Okay, that is your bending load. Strictly speaking. Okay? So if you look at this, that's why you say I feel that you are not very interested. Wait, I need to go through this. Just give me a minute. Yeah, can. Yes. Just now a question was asked, hey, class. You all are all in your respective team, right? You know, you are all in your respective team. The reason is because this way, right, it will help you to help you all to work better. You know, this what am I trying to say? Yeah. So each team will have the same design. It's okay. Okay, so that you all can help each other. Like I say, because I think the problem with the design part of it, right, is coming out with a design which need not be right or wrong. Just not we see a lot of different design. Okay, you can so long as you have a beam design, you have a truss design, you have a plate design, that is more important. Okay. Or report different. You must have the same design, but you must write your own report, and you must clarify on the report. You know, like later I went through a few examples. Okay, I just quickly went through this and finish with it. Okay, so this is the S11. Remember, just now we have run the S11, right? So you see, this is your S11. You can see that we have restricted in this direction now. Just now, so we can see the stress is actually quite perpendicular to our restriction condition. That's why it's important to do it S11. I'm not going to change it back to the other one that you see here. Okay, but you can see that this is S11. What else I need to say? Yeah, the bending stress one, right? Okay, the bending stress. Let's take a look at the bending stress. We'll put it side by side. Okay, then we put one as the bottom one. Okay, you can see the bending stress, right? In this case, right? The middle is about this will be in Pascal, correct? This will be Pascal. So it's 92 megapascals in the middle. Okay, at the bottom. This at the bottom, yeah, negative. So this is bottom, surface negative. Okay, and it's about. Sorry.
The 3D case where it is showing this case. I mean the exact surface, this direction both. In the visualization of the
I didn't tell you. Charlie.
Ask the what? Ask the 30. Where's the 30?
Right side is
Last this. Last side. Get 2 marks. That's right.
So you see, can you see? Is it clear enough?
Yeah.
Can all? So you see, this is 92 megapascal, and this is 92 megapascal. So you see, this is a pure bending equation. This is negative 92, this positive 92. Do you see that? Positive, negative. That's why this is a pure bending in the middle here. Do you see that? And I'm trying to illustrate here what I'm trying to illustrate. You can't really tell it, because S11 will always be in this direction or in whatever coordinate direction. Okay, you can't really tell what's the bending stress. The bending stress is always the stress, the difference in the stress. You know, like for example, inside a member, right? Inside a member, you can't really tell what's the bending stress. If the stress across the plate, right, is like this, your S11 is always like this. Let's say for example, that is a pure axial stress, correct? But let's say for example, in this case, you see, we have positive what 92, 92, okay, 92 megapascal, okay, and at the bottom we have a negative 92 megapascal. It's a pure. Then it becomes a bending issue, a bending problem. Do you see that? Okay, so there's no bending stress. The bending stress is seen from the S11 at the top and at the bottom. Okay, surface negative, surface positive. Okay, in our case, if you watch the video, right, you don't really need to know what is the bending stress. I say no, you don't need, because as an engineer, right, actually what your concern is whether the stress exceed your U strength or not. Okay, so be it positive or negative, just take it as one absolute figure. If you remember your material stress strain curve, your material stress strain curve, right, we do it both way. Okay, we do it both way, your x and y. So we do it this way, right? Your negative and your positive, you put it at the same as sigma y. That's why it doesn't really matter. You get both. Okay? That is all I want to say. The take note is the S11 is in this direction in this case. In your model, you are not going to assign a separate coordinate system. So S11 is your Cartesian coordinate. Okay? Anything else? Yeah, okay, I want to show you the 3D just now. Okay, so we can take this, and you can see that it's dividing like this. You see that? Okay, this is dividing like this. Okay? So divide the shape. You can render this, you can render this, go to render the thickness profile. And you can see that, you see that. Okay. Does it mean that in reality you have a thickness? No, it doesn't. It's just showing you that, okay, it's just showing you that that is simulating a 4 millimeter thickness here. Okay, but then it's not. If you do it in a 3D, if you do it in a 3D model, right, you will see just now the red and blue stress directly on the model. Okay, but because we are doing it as a plate model, you only have one reference point, one reference surface. You need not on the block. Okay. Okay, is it? I will. What I intend to show you now, right, which I think is difficult to do it in the online setting, is to let you know. So everybody, are you clearer in terms of the plates and the shell model as compared to the beam and truss model? Anybody got question? What is the main difference? You know, I always like to do this. Compared to your beam model and your truss model, what is the difference from the beam and truss model? Number one, you need to assign the material orientation, just like your beam model, correct? So you know where is your S11, correct? If not, how do you know just now this S11 is which direction? Then you just plot S11, S12, no, right? You need to know exactly what is S11 so for you to rationalize it. Number two, number two is the same, is the S11, to take note that the S11 is based on your coordinates, your Cartesian coordinate. Of course, the other things like, you know, like in terms of the material property, you need to show the thickness, in terms of the element type, you must use a shell 4, S4 or you always use S4 in this case, S4 shell element. Okay, that is the main difference. Unlike the beam model, you only have one stress, S11. Alright, in this case, you will have two. Okay, and in the 3D space, of course, you have three. That was it. I just wanted to explain to you, right, what is a plane stress and what is a 2D solid model. What do I mean when I say it's a plane? I want to explain to you what do I mean when it is a 2D solid model and it's hard to read.
Thank you.
What is Hey, are you all okay to stay like 10-15 minutes? Are you all okay with that? And because actually, by right next lesson, you all also got to stay until 6, right? So you all must be okay to stay until 6, right? But then I will next until 6, it's just 10-15 minutes. Okay, but I thought this is easier to explain like this rather than in the online where I need to assume that you understand. Okay, can you all take a 5-minute break? You all take a 5-minute break?
I'm reading my house there.
Just need another.
Hey, something. Is this yours? These wires right?
I'm buying burger, Tupper bag burger.
What?
Not Tupper bag burger.
Burger?
Yeah. Tupper bag. Wow.
Okay, hey, class, as I find my material,
The model.
wait. Now, you all are still fresh. I want you to think about it. In your con rod model, how are you going to do it as? Because now we have done 3 already, right? Beam, truss, and your plate, correct? So how are you going to do it in the plate? If it's a plate model, how would you do it? You don't think about it. If it's a plate model, how are you going to do a plate model? You know what I'm trying to say, right? Just now we did the beam, we did the truss. Now for plate, how are you going to do it? Can you think about it? You all try to sketch something, you all cannot think like that one night. Come and die, come and you cannot practice maths by thinking about it. You all need to draw something, draw.
Plate or plate?
I believe this is it. Then you just extract the bones. That's all. Then if you want to draw cross, right, maybe it's just like that.
Cut. Without the circle lah.
But then 3D, you need to do something with you need to do something at the side. 2D.
Yeah. So basically, chamfer, you can turn them into a rod.
Yeah. It's either we turn this to a rod or we turn or do some curvature to the
I think that's not you need to take it because this one center line is the same. So basically your center line need to be the same as this. This one right? Smaller.
So I think can be the same as the thickness also.
One here, this one right, need to be small little bit, so we need
So can save more money.
no, rod. So what? Yeah,
Hey, you all must be able to think of it. I said I found it already. Okay. Okay. You all want class. Do you know what I'm trying to say? For the third one is what they call the shell model. They call it plate model. Huh? Shell model is it? Shell or plate? They say what?
Third one is 2D.
2D model. They never say shell or plate. Or they say 2D solid. And this is important. Next lesson is the last lesson. So by then you all should be very familiar except for the solid model. You don't know what I'm going to say. You don't need to think about it that serious. You don't do it in class, then why you want to do it? What is the third one?
2D solid element.
Third one is 2D solid element. Yep. Okay, so I need to share a little bit of this first. I will end off this lesson, okay, explaining what is a 2D solid element, which is quite similar to what we do for the plate and shell. And I would want to take 5 minutes of your time after I finish to let you all discuss what is your geometry going to be for the 2D solid. Is it okay? Can we do that? Okay, then it's easier. For the last lesson, I can just go through the solid model with you all, what you all want to do for solid model, and I can have a little bit of, I can prepare you all for the exam also. Okay? Can Okay, this is the 2D solid element. 2D solid. So what is a 2D solid? If you look at this, just now we talked about is what? We could do it as the easiest way, of course, is to do a 3D model, correct? But sometimes I can simplify it significantly to have as a beam model, 1D beam model, correct? But I just need one dimensional, okay? I need to create a section and an area. The other way I can do it is as a plate or a shell model, correct? Without a prescribed thickness. Remember this, is a prescribed thickness, okay? However, when it comes to certain structures, right, I can also represent it as a 2D solid, whereby I don't really prescribe a thickness to it. What do I mean? Like for example, if you have a bracket like this here, right, there's two ways. One is as a bracket, or when you have something very long. Okay, so one is as a plane stress. So typically it's something very thin. Let's say for example, if you have like if you have a wall, let's say I have a wall, I'm trying to apply a load onto the wall itself. Okay, load onto a wall like this. It could be a plane stress model, something very thin. Okay, it could be a plane stress model. Or let's say for example, you have dam, you know, like your, not like the Singapore, the Kranji dam, but something longer, you know, those very long build up dam, right? It is very long. Or you have, you know, like along the entire river, you have those dam, right? It could be a plane strain model. What does it mean? It means that in the plane stress model, right, you assume there's no deflection, there's no deformation, right, in the out of plane direction. But in the plane strain model, you're assuming, right, there is no stress. There's no, you're assuming, sorry, in the plane stress model, you're assuming no, you're assuming no displacement, correct? In the plane strain model, you're assuming no stress across the entire thickness direction. So essentially, it means what? If it's something very thin, it's plane stress. If it's something very long, it will be plane strain. Okay, do you get that? How does it do, right? From the mathematical point of view, right? I used to have a matrix for that.
Basically, cross section, right?
Okay, so you assume it's the thickness direction, right? So I assume there's no stress in the plane stress direction, right? You see the sigma z is in the thickness direction. You assume there's no sigma z. But in the plane strain, right, you're assuming there's no epsilon z. Okay, what is sigma z? It assumes 0 for the plane stress. For the plane strain, you assume there's no strain in our plane direction. Okay, so one is for something infinitely long. One is something that is very thin. Why? Because imagine if I have something very long like a dam, right? Imagine I have a dam like this, right? If I was to push it together, correct? Because they are so long, right? They will pull each other. Everybody will restrain each other. Do you see that? Let's say this is the dam. Let's say this is the dam. Okay. Let's say this dam is going infinitely long. I'm going to push. You have the water level coming up, pushing everything against it. Correct. So do you have any strain in our plane? Why not? Because all of them are restraining each other. We are assuming this hypothetically, right? Infinitely long. So everybody is holding each other in the thickness direction. That's why there's assumed no strain. Okay. Inversely, very thin, something very thin. Let's say something very thin like this. Okay. And I'm going to, if I'm going to compress it, there you go. Something very thin. This is, let's say this is the thickness direction. Something very thin. I'm going to compress this. Okay. The thickness direction, right, is so thin. That means there is no stress in outplane direction. Is it easier? The strain is easier to understand, right? The strain you all understand, right? The strain you all understand the part. Okay, it's the stress part. You all understand the stress part of it. Because it's so thin. Because it's so thin, that's why because it's so thin, that's why it's free to everybody. You have the Poisson effect coming in. It's free to be formed in outplane direction. Okay, that's why there's no restraint. But in the plane strain, it is totally restrained. That's why there's no strain. That means you have the maximum stress. But in the plane stress, it's free to be formed. That's why there's no stress. So it's quite inverse. So the plane stress and plane strain is quite inverse in the thickness direction. Just remember the main thing is, I think as a whole, right, you need to remember is for the plane strain is something very thick, like a dam. Always remember it as a dam. For the plane stress is something very thin, and the reason is because of the restraint in our plane. Okay, very long. You have a lot of the member itself are restraining each other. That's why you're restraining each other out of plane. It doesn't move. Okay, this is the other way. I don't consider thickness at all because there's no stress. Okay, so but the model of this, right, essentially is you still model them as a 2D element. The matrix is different. I thought that this is interesting. Why is this easier? Why is this still more efficient than compared to a 3D model? Because it makes an abbreviation, right, in your statement matrix itself.
Base model 再講one block
So you see, this is your. So you see, this is your full entire statement matrix, right? For your. This is the full entire statement matrix for your 3D model. Okay. My right, you will have your sigma x, sigma y, y. Okay. Sigma z, z. Again, they have sigma x, y, sigma x, y, sigma y, z, and sigma x, y. Okay. So you have your 6x6 matrix in a 3D solid. Correct. The difference is that when it comes to plane stress, plane strain, you will directly omit out. Let's say, for example, in this case, this is a plane stress model, whereby they omit out the sigma x, the sigma zz, sigma zy, and your sigma zx directly. So that's why it helps to reduce compared to the 3D model. Okay, and that's why you can model it as a plane stress. Then that is why it's different from your plate and your shell model, whereby you only have the 2D. In your 2D model, right, you only have sigma x, sigma yy, and sigma xy, but then you don't have this 6x6 matrix here. Okay? But in this case, they omit out this part. That's why it is still easier compared to your 3D solid. Inversely, when it comes to your plane strain model, right, they will take out is the epsilon zz, epsilon, not take out, they will assume 0, epsilon zy, epsilon yz, and epsilon zx as 0. So it will still be easier compared to your 3D solid. Okay? So in your case, when it comes to the cone rod, this is the most important part, right? In your cone rod, right, what will you be using? A plane stress or the plane strain element?
plane stress.
Who says plane stress? Put your hand. Who says plane stress? Put your hand. Put your hand. Who says plane strain? Put your hand. What do you say? Cannot say don't know. Hey, plane stress. Put your hand quickly. Plane stress. Hurry up. Hey, ending already up. Plane stress, put your hand, plane stress. Plane strain. Okay? Like I say, in a plane strain, you're assuming that there's infinite restraint in our plane direction, correct? In a plane stress, because it's very long, okay? That's why everybody is restraining each other. Plane stress is opposite. Plane stress, you're assuming that they don't restrain each other. You know, like for example, if a cube, you press it, right, you have a Poisson effect. That's why your out of plane direction actually is restraining it, you know. But in the plane stress, I do just now we showed, right? You know, we're assuming sigma zz is zero, so it doesn't, the stiffness in the thickness dimension doesn't influence it. That's why it is denominals, right, to a very thin member. So in your con rod, it should be a thin member or a thick member. Thin member. So I'm assuming there's no restraint in the thickness direction. So it should be what? Huh? Who says it's plane stress? Who says it's plane stress? Plane stress. Plane strain. So it's supposed to be a plane stress element. Okay, because it's supposed to be very thin. Your con rod is supposed to be very thin. Okay, assuming what? There's no restraint in the thickness direction. Okay? Unlike a dam, you see that like a dam,
Then the con rod can redesign the thickness. That is to say.
no. There is a difference between I neglect the thickness and the thickness is less significant. There is a difference. That's right. There is a difference between saying that I neglect the thickness, okay, and the thickness has no restraint effect. There's a difference. Then you need a thickness because you have a section modulus, so you need the thickness for that. You can't avoid the thickness. It's just saying that, like I say, the plane stress, and in the learning in the online module, I will show you from a cantilever beam, right? How does the actual shell model compare against the plane stress and plane strain for a thin member? Okay, but I'm saying is that the plane stress, plane strain is a reduced model for a 3D solid because it directly omit out your sigma x or your sigma zz or your epsilon zz. It's just a reduction, make it more efficient. Okay, so it's it's a hypothetical one. To be very honest with you, in the industry, right, we don't use plane stress, plane strain. In the industry, it stays as a very academic one. Personally, because I'm assuming, and there's no way to, and there's no hypothetical model for that, you know. In a shell model, I'm just assuming that you have only degree of freedom in the xy direction. Okay, the zz is linearly interpolated. Remember, just now we showed the S11 at the top and the bottom. There is still a stress due to the bending also. But in the plane stress, right, there is no deformation in the thickness direction, alright? Because it's a 2D solid, right? So it's a 2D space, alright? But I am just assuming that it behaves like a plane stress and plane strain through that matrix I will show you just now. So there's no really relevance in the actual solution. So it stays very academic, but it is very efficient. It's very fast. It runs very, very fast. Okay. If you ask me, it serves as the upper bound or lower bound. That means your maximum result. Maximum plane strain will give you the maximum stress. Plane strain will give you the maximum strain. Right. Imagine if I have a piece of paper, right? If I have a dam here, right? I want to know what's the maximum stress on this, right? I say just now, the most restrained condition will give you the maximum stress. If you pull it, like, let's say for example, if I want to deform this same load, same load. If I have a piece of paper, I have dam here, I want to displace it as a cantilever. Okay? If I don't pull this at each end, will the stress be higher as compared to if I pull it at this end? Which will be higher? If I pull at this end, right, and I push this, right, same force, pulling at the both ends will give you a higher stress. Agree? You agree? You agree? Alright. As compared, I don't pull the end, I just displace this. Same load, this will give me a lower stress. So that's why the plane strain, right, will artificially give me the most conservative stress. Okay? Likewise, for plane stress, you give you the most conservative strain. You know, because let's say for the same load, I'm let's say applying 10 kilonewton. The plane stress will give me the highest displacement compared to a plane, compared to the actual condition. Because in actual condition, I will have some sort of restraint on each end. So you reduce because of Poisson restraint, you know, Poisson effect, you restrain it in the outward direction, reducing the deformation. Plane stress will allow me to deform the most. So it is even though it is an artificial type of result, you give me the upper bound and lower bound for the strain, under the plane stress condition, maximum stress in the plane strain condition. Okay? I think that was all I want to show. I just want to run through because we are on the beam and it's a truss model. Can I just quickly run through with you the past year? How do we prepare? How do we answer that? Are you okay with that? Can? I want to point out the reason why I do this is for a reason, for a purpose. Because in your exam, right, you will have two parts. First part is you need to create. Let's say we just talk about beam and truss. You know you have three parts. First is a calculation. Second, you need to have a model, of beam and truss. Third, you have a shell model, correct? But for your beam and truss, you need to have two parts. First part is you mathematically use the model to calculate, let's say for example, maximum stress or maximum displacement. You need to have one. The second part you need to discuss is the discussing part that I want to show you. And the part is 50-50. So getting the model right, uploading it, maybe get 50% right. The other 50% is this. I try to do it during the online lesson, right? I try to explain during the online lesson. I'm not sure how whether you all have survived out of that stage. I try to explain it right. In the discussion, this is where you need to demonstrate your understanding. That's not that we say. When it comes to the comparison, you bring up things like, for example, your beam, your truss element, what will you do as an engineer? You don't just base the result, that's it, full stop, no. You look at the result, whether it makes sense or not, correct? So you see the result relatively close. Okay, which one will give you a higher displacement, beam or truss? Anybody, quickly? Which one will give you a higher displacement? The result is here. Actually, I have a typo, my apologies. Yeah. This is obviously a beam model, this is a truss model. Okay? Yeah, it's clear. Okay, I turned it wrong, Okay, anyway, this is obviously the truss model. Okay? And this is obviously the beam model. You look at the deform shape, you know which one is the truss, which one is the beam, right? Okay. Yeah. Yes, which one have a bending? Alright, so obviously this is the beam model, obviously this is the truss model. Which one should have a higher displacement? Who say beam? Look at the result, man. You all look at the result, so you can give me the wrong answer. Which one say truss? Can you read the result? Which one is higher? Which one is higher? Look at the result, so you can give me the wrong answer. Who say truss? Who say trust? Hurry up, Who say trust? Why? About why? Think about what I said just now. Think about what I said just now. Think about what I said now. The more restraint you have, correct, will give you a higher stress. Correct? But lower displacement. Make sense? Make sense, right? Make sense, right? The more restrained you are, the stiffer you are under the same load, under this load control condition, under the same load, it will give you a smaller, if you are more restrained, it will give you a lower displacement, correct? Okay, I'm just going through roughly on how you should answer this sort of discussion. Remember, if I have two models, you need to think about things like this, okay? Truss, slightly higher. Why? Because the truss model only handle the axial stiffness. It only had axial stiffness. Remember just now when we run through this, right? It had the same area. So we have the same axial stiffness, but in addition, it had the bending stiffness based on the section modulus IXX, right? So this one has the additional bending stiffness, whereas this only have longitudinal stiffness, correct? Only the axial stiffness. So that's why here, you see that it has a slightly higher displacement. Make sense? Imagine, let's say for example, now you don't forget about this. I'm just going to pull a rod. Okay, first rod have axial stiffness. Second rod have the same axial stiffness, but on top of that, it have a bending stiffness under the same load. Which one will give you higher deformation? It will be the one with the lesser stiffness. Agree? So that's why this will give you a slightly higher displacement. So you need to bring up things like this in your discussion. Make sense? Okay. For example, like this, U1, because I go through this a couple of times already, we expect this to move slightly to the right. Makes sense? So this one I'm not going to say. And things like, for example, stress. Okay? This will give you a slightly higher displacement. So which one will give you a higher stress? The beam or truss model? Which one?
Beam.
Huh? Who say beam? Who say truss? Correct. It's always inverse. The one with the higher displacement, right, will have a lower stress. The one with a higher, with a lower displacement, higher stress. Think about it, very intuitive one. If your system, right, any system, right, allow you to, the movement itself, right, means that it's reducing the load. Okay, it's dissipating the load. Let's say if I apply something, if I have a very stiff system, I compress it. If you allow it to compress a lot, that means the stress is actually dissipated a lot already, because through the displacement, it already dissipate out the external force. If it's something very stiff, you only have a little bit of displacement, then the stress will be higher. Make sense? Okay, that's why this will be slightly higher, not significant, marginally higher. Okay? That was it. I will run through just show you the report from last year when it comes to beam and truss. Okay, all this is the same. You all will do something like that. Like I say, always start off with a figure. Show me you know what you're going on. Okay, then you will come up with the geometry. Okay, don't assume, you don't just sketch the frame and expect me to know what section modulus, what section you are using. Because it could be what? It could be a circular, it could be a square, it could be a rectangular, it could be a polo section or whatever. Be clear. Okay. Then in this case, you see that I actually ask them to optimize for the different dimension, different profile by right, but it's okay. Yeah. Then need to come up with the what? With the load and the boundary condition, just like your direct system method, right? Same as per the online lesson, you see, you need to present the most meter stress, S11, U1, U2, RF1, RF2, same, correct? This is a truss model, so you only present one set of misses and one set of S11. If it's a beam, you need to present both the top and bottom. I'm coming to a point very quickly that you all will be starting. Okay? Huh? No, later using so this, okay, just remember, so this for the truss frame, right? So it's a very simple, it's a little bit like the hoist one that we do, except the bottom is flat. But this is skewed because it's a bicycle, right? So but it's still a truss. It still can be done as a truss. Isn't it? It still be stable as a truss, alright? Okay, so this do a truss. Other than they do for the beam, this is a beam order. So because this beam, right, you see here, this beam, this is the wheel, right? This is a beam. So there's no way that this can function as a truss. You will need to take bending. So this would be a beam model. Make sense? Huh? Huh?
Isn't easier than the current assignment?
On hindsight, now it appears easier. Last year, then they also compared 4 or 5 years back. The 4 or 5 years back is easier. The comparing never ends. Seriously. Yeah, they share. Okay. Wait, you see, in the trust model, right? You see what's happening? Can you calculate by hand? By hand, what is the stress in each member? Can you do that?
Can is can.
Huh?
Troublesome.
You need to do that. That's why as an engineer, if there's a way for you to calculate the result, then you need to do that to show that your result is correct. Trust model, you need to do that. Okay? Not difficult. Not difficult. If you have two support, right? If it's doable, it's doable. Okay. You'll see whether it's doable or not. I will check if it's doable, I will comment it's doable. Okay, so you have to assess it. In this case, it's doable. Okay, because there's two reaction, there's a reaction force. You apply the load here, right? So you know what is the reaction force here. You know, right? You will know, right? Okay.
Yeah.
Then you will know based on the angle here, you know the load distribution between here and here. You can find out what is this stress here, what is this stress here. Correct? Easily, you can find out the moment, sum of moment across the entire system. From there, you can find out the individual reaction load. From the reaction load, based on the angle, you can find out the individual member load. From the member load, you can find out the member stress. Correct? Alright. You check whether the result makes sense or not. Compare to Abacus result. Your analytical solution compared to the Abacus solution. Margin of error. You see that this is only doable for a trust system.
So
Meaning,
we
no
don't
way,
do the
because
trust
of
can
the
already.
bending. Huh?
So if we don't do the trust, then we don't need this.
You don't want the trust mark allocation, is it?
Oh.
Huh? You don't need, is it? Or you?
Need.
Huh? You don't need or what?
Need.
Need then you need. Okay? But you see, only the trust system you can do it because it's very important because the trust I do need to care about the amount of rotation. In order for you to find out the bending, you need to account for the amount of rotation, which is impossible to calculate. Okay, that's why the trust can do that. That's why the trust is so powerful. Okay? Last part. Last, I don't get excited with the calculation. You continue first. Huh? Let me show you the discussion. I just want you to have an idea of what to discuss. No. I think it is important because I don't want the Abacus to do software kind of conclusion. So I want you all to take a look. And then you can see the thing that I discuss is always the same one. Whatever I say, you all can just okay? You see? Compared to the truss, right, the beam are able to support shear and bending moment. Okay, to have angular deformation. While the truss only have axial load. Okay, so I have such bending force. Yeah. So things like this. Yeah. Then taking a closer steel material is closer to the design requirement. Meet the particular compliance limit. So you need to bring in like your design limit, things like this in your discussion also. Okay. And also in your exam also you need to bring in things like this. Okay. So try to prepare certain amount of the discussion. You see, it's always the same. Just now we talk about plane stress, plane strain. Plane stress is what? For a very thick or very thin member. Huh? Thin member. Plane strain is for very what? Things like this. Prepare beforehand. Just plug it in. Okay, don't plug the wrong thing. Some people plug the wrong thing sometimes. Yeah. Okay, plug it in. Prepare a little bit of this thing. It's always the same thing. I already told you, beam, truss, one model. Plate, 2D solid, another model. So prepare things like this. Okay. Then it will be easier. Okay, yep, that's all. Thank you. Right.